Chapter number 11, that's about three-dimensional geometry. Same chapter we already studied in 11th standard. Now here in this chapter we are going to study two things. One, that is a line in space, that is line in R3. That is one thing we are going to study. Line in R2 you already studied in 11th standard in coordinate geometry. And the other one, that is plane in R3, that is plane in space. Remember, two things we'll study. Now, if you just recall, direction cosines and direction angles of a vector, direction cosines and angles of a vector, that you know, that we did in the previous chapter. Now here we want to define as the first point, that's a direction cosines as well as angles of a line in R3, remember. So let's see this. The definition is more or less same. So we start with your 3D geometry, that is we consider three coordinate axes here. Let's consider three coordinate axes, as you know. So here this is x-axis, let's call this as y-axis, and this is z-axis. We consider a line through origin, so let's take this be a line like this that passes through origin. Line in R3, line in a space. Okay, so here let's take this alpha be the angle of the line with x-axis, this angle with y-axis as beta, and angle with z-axis as gamma. So here this alpha, beta and gamma, these are the angles of a line with the three coordinate axes. These are known as, you know, direction angles. So alpha, beta and gamma are the angles of the line with the three coordinate axes, of the line with axis x, y and z respectively, with these three axes, you know, respectively. That much we know. And therefore this L equals to cos alpha, small m equals to cosine beta, and small m equals to cosine, small n equals to cosine gamma. You know, these are called direction what? Cosines. These are called direction angles. Here this cos alpha, cos beta and cos gamma, these are called direction cosines. Are called direction cosines. Direction cosines. Usually these three, cos alpha, cos beta and cos gamma, represented by L, M and N. And even, you know, this is very standard relation here. L square plus M square plus N square equals to always 1. That is, if alpha, beta and gamma are direction angles, then this cos square alpha plus cos square beta plus cos square gamma, that is always, you know, 1. Where what is this alpha, beta and gamma? These are nothing but the direction angles of the line. Direction angles. Right? That much we know. And the same thing also holds true for a line. We have defined such things for what? You know, vectors in the previous chapter. Now here, these are the direction angles. Okay. Now for a vector, if you remember, if this is a vector, for example, let's take vector R with components as, let's take A, B, C. You know, these are the components of this vector. Let's call the vector R. Then direction cosines you can write very easily. How do we write the direction cosines of this vector OA? You know it. Unit vector in the direction of this. Direction cosines of this vector OA, that is nothing but what? The first component upon its magnitude. What is its magnitude? That is a square plus b square plus c square. What about the second one? B upon its magnitude, that is root of a square plus b square plus c square. This is small l, this is small m, and this is small n. And what is that? C upon root of a square plus b square plus c squared, right? This is nothing but l, this is nothing but m, and this is nothing but the n. You know it. You can verify l square plus m square plus n square is 1. You also know that this is just unit vector in the direction of this given vector. That is nothing but the direction cosines, which we know very well. But if I consider line instead of this vector, so I may consider the opposite direction like this. Okay, suppose like this. So now this becomes a line L. Then you may have opposite direction. So in that case, the direction cosines of this line OA, which is equals to line L, that is now this is plus, but if you consider opposite, you have plus and minus here. So here plus or minus here. What about this? Plus or minus. So direction cosines of this vector OA, that is nothing but the line L, which is given by plus or minus this upon its magnitude, plus or minus second component upon its magnitude, and plus or minus c upon its magnitude, remember. So in case of entire line, you may have plus or minus. For vectors, you had, as I mentioned, just one directed. That's one thing. So this way we define the direction cosines for a line with plus or minus sign. Fine. Now if you have 2 points on the line here like this, let me write direction cosines of a line through let's take P of x1, y1, z1 and Q of x2, y2, z2. That is, the line passes through these 2 points. You are not given the direction of this line. Here, direction of the line you were given, that's vector r. So here it's like this. So there is a line that passes through one point P, the other point Q here, remember. So here either you can take the direction as this vector PQ, or you can take as vector QP also, remember. That's not important. Right? Either way you can take the direction. So suppose let's take the direction of this line, direction of line PQ is, you can take just as a vector PQ. Now you know how to write the position vector of the vector PQ. That is Q minus P. So how do I write the components here? x2 minus x1, comma, y2 minus y1, comma, z2 minus z1. Right? How I have chosen the direction of this line? That is vector PQ. You could have taken QP also, remember. That's not important. Direction cosines remain same. So then you can write, therefore, direction cosines equals to direction cosines of this line PQ as x2 minus x1 upon the length of this, that is length of vector PQ, comma, y2 minus y1 upon length of the vector PQ, comma, z2 minus z1 upon the length of the vector PQ. Fine. This way we can define. It's like previous case only, but here the only extra thing you did, that's the direction of the line. The direction you were given, that is this, for example, vector r. There it was ready. Here it was not ready, so you got it by considering vector PQ. Again, I'm telling you, I already told you that you can consider QP also, because in case of this, you know here, let me emphasize this, you have in general what? Plus or minus here. So plus or minus, here plus or minus. So whether you consider this as a vector PQ or QP, your final direction cosines remain same, remember. Fine. So plus or minus first component upon its magnitude, second component upon its magnitude, and third component upon its magnitude. That's what we have. Now let's see exercise 11.1, that is just based on this only. First question, a line makes angles alpha equals to here 90 degree, beta equals to your given 135 degree, and gamma equals to 45 degree with 3 axes. Find direction cosines. So you know how to write here direction cosines. Angles are fixed, remember here. Direction cosines, L equals to cosine alpha, M equals to cosine 135, and N equals to cosine 45. Right? Cos alpha, cos beta, cos gamma. So this is 0. How do we write M here? You can write 90 plus 45. So it will be in third quadrant, and you have minus 1 by root 2. Just verify. And what about N? That is just 1 by root 2. So therefore finally you have 0, comma minus 1 by root 2, comma 1 by root 2. These are nothing but the direction cosines. Fine. Now what about next question? There, what's given in the next question? You are given that direction cosines of a line makes equal angles with the coordinate axis. So what's given to you? You are given that alpha equals to beta equals to gamma. Fine. So therefore what you will get here? Cos alpha equals to cosine beta equals to cosine gamma. And therefore what you will get? L equals to M equals to N. And this is always true, you know. L square plus M square plus N square is 1. So if you place L here, you have 3L square equals to 1. So what is L here? Plus or minus 1 by root 3. Here you can have plus or minus. Here you cannot have plus or minus because here angles were fixed, remember. Fine. So L is plus or minus 1 by root 3, M is plus or minus 1 by root 3, and N is also plus or minus 1 by root 3. So therefore, this is the final point. Direction cosines equals to plus or minus 1 by root 3, comma plus or minus 1 by root 3, comma plus or minus 1 by root 3. L, M and N, and all are equal here. This is same as M and this is same as N, remember, because these 3 are equal here. We had one more question like this in the previous chapter, so you can just recall that also. Next question, if the line has direction ratios, what are the direction cosines? Direction ratios means what? Just direction of the line, remember. And what do we understand by direction cosines? Unit vector. So you just need to make it unit, nothing more than that. So here what is given to you? Direction ratios. That means direction, remember, direction ratios, that is minus 18, 12 and minus 4. Fine. So if this is a line, for example, and let's take this as a vector L bar, this is a direction. So it is minus 18, 12 and minus 4. It's a vector in the direction of a given line. That's sometimes called direction ratios. What about direction cosines? We make it unit. That much only you need to do, remember. So first I'll get its length. Okay, so what's the length of this? 18 minus 18 square plus 12 square plus minus 4 the whole square. So what we'll get here? You know, just add them and simplify. So this is just 484 and which is 22. And therefore now once you know this, you can just write direction cosines. So you can write direction cosines as here, you know, it is minus 18 by 22 comma 12 by 22 comma minus 4 by 22, so which is same as minus 9 by 11. Then this is 6 by 11 and minus 2 by 11. Now in the next question, show that these 3 points are collinear. There are various ways to show. Let the points be 2, 3, 4 here. B be minus 1, minus 2, 1, and C be, for example, 5, 8, 7. Right? You want to show that these 3 points are collinear. We had such questions even in 11th standard and earlier exercises also. How do we show this? Not difficult. You get the direction ratios for this and direction ratios for this. You will see that they are multiples. So the vectors must be collinear. Right? So find the vector AB. You will realize immediately. And vector BC. You will note that these two will be multiples. What about vector AB? B minus A. Minus 1, minus 2. So minus 3. Minus 2, minus 3. Minus 5. 1 minus 4, minus 3. What about BC? 5 plus 1, 6. 8 plus 2, here 10. And here 7 minus 1, which is 6. So you must have noticed, you multiply this by minus 2, you will get exactly this. So vector AB equals to k times vector BC. Right. Therefore, these two vectors are collinear. Where k is here, very easily you can see it is minus 2. Right. This and this are collinear vectors, and therefore these points are collinear. In fact, here vectors AB and BC are in opposite direction. It's like this, for example. Here this is vector AB and BC will be in the opposite direction. The BC might be like this, remember. This is BC, this is vector AB, like this. AB and BC are in opposite direction because K is minus 2 here. Multiply this by minus 2, you will get exactly this. So these vectors are collinear. We had earlier such question. Okay. Next question, question number 5, fifth one. What about in this question? Find the direction cosines of the sides of a triangle whose vertices are this. So in that case, you will be having 3 possibilities, remember. In the fifth question, you have a triangle here. Let me call this as triangle ABC. What is A here? 3, 5, minus 4. What is B here? Minus 1, 1 and 2. And what about C here? That's minus 5, minus 5, minus 2. Fine. This is given to you. What do you want? You want direction cosines of the sides of triangle, remember here. So the one side here, sides are this. Which are the 3 sides? You know vector AB. You can take the BC and you can take the vector CA. So first for this side, for side, let's take AB here. So first you need to get the position vector, which is B minus A, you know. So minus 1, minus 3, minus 4. 1 minus 5, which is minus 4. And you have 2 plus 1, which is nothing but 6. And its magnitude. Direction cosines means always unit vector, remember. What its magnitude? So minus 4 whole square, 16. Minus 4 whole square, 16. Plus 6 square, which is 36. So what we'll get from this? You can take just 4 outside, it will be 2. If I take 4 outside, here you are left with 4 plus 4, 8. 8 and here 9, so we'll get the root 17 here. So it is 2 root 17, remember. Fine, and therefore direction cosines of this side, cosines of the side AB here, that is equals to minus 4 upon 2 root 17, minus 4 upon 2 root 17, comma 6 upon 2 root 17. And simplify, you will get the minus 2 upon root 17, comma minus 2 upon root 17, comma 3 upon root 17. These are the direction cosines here for this side vector AB. Similarly, you can do for this as well as this. Right? That's not a big task for you. Now we discuss some more theory related to lines. So here first point is equation of a line through a given point. You are given a point here, given point, say A of this vector A, and having direction of the line that's a parallel to some vector, having direction which we write here parallel to a given vector, say B, is given by this expression. What we are writing here? We are writing equation of a line in R3. Remember, we are talking about space here. That passes through which fixed point? This vector A, and parallel to vector this B. That means having this direction, remember. What's the direction of this? That is vector B. So if I just show you here in R3, let me just represent in Cartesian plane here. So this is x-axis here, this is y-axis, and this z-axis. We have a line here like this. This is a line in R3. Let me call this as line L. So direction of this line, that is this one, which is parallel to some given fixed vector, which is vector B. And this passes through one fixed vector, that is A. So here this vector A is a point on the line, and direction of this given by this vector B, remember. Fine. If you remember in R2, to get the equation of a line, you used to use these two things. One is point and the other one that the slope. If you recall the point slope form, you were using point and slope to get the equation of a line in R3. Right? In R2, you were using point and slope, if you just recall the point slope form. In R3, we are going to use the fixed point and the direction of the line, or you can say that a vector that is parallel to the direction of the given line. So parallel to this vector B. B is sometimes called the direction of the line. Now you need some variable point on this line. So I'll take that variable point as, for example, here vector R. So R is any point. Okay, now clearly you can see that this vector AP and vector B are parallel. Is it? That you can see clearly in the diagram itself. Which two vectors? Vector AP and vector B are parallel. So they must be multiple. So say multiple, instead of K we call that lambda here. Now what's the position vector of this? That is, position vector of P is vector R minus vector A equals to lambda vector B. So from this we write here vector R equals to, this is any variable, remember, vector A plus scalar, lambda is a scalar, remember, into vector B, where lambda belongs to R. This is the vector form of a line in space, remember, which you need to remember. Vector R is equal to vector A plus lambda into vector B. What is this R? R is any point on this line, remember, it can be any point on this line. This is sometimes called the variable point. What is this? This is fixed point on the line. Lambda is any scalar. And what is this vector B? vector b that's represent the direction of a line, or a vector that's parallel to the direction of the line. So this is sometimes called the vector form of a line through the fixed point vector a and having direction as a vector b. Fine. Now if I write in form of for example Cartesian, so Cartesian form will be this here. This is sometimes called the vector form. So we need to take the components of this vector r, which you can write I x I cap y j cap plus z k cap, which is x y z in general, you know, because this is any point. In R2 we used to take x and y. Here we take x y z. This is a fixed point, so we'll take x1 y1 z1. Here x1 y1 and z1. Remember, this is a fixed point, so x1 y1 z1. And what about the direction here? That's vector b. That is given by what? Let's take I cap plus b j cap plus c k cap. So here direction will be this a b c here. Direction of the line will be this. If I place these values here, I'm just placing the value here. So what is the left hand side? That is x y z. Let me write here. So x y z. On the right hand side you are going to add the components. What's the first component? x1 plus here lambda a. Then you will get the y1 plus lambda b. And what about the last one? That is here z1 plus lambda c. From where we are getting this? From this equation, from this vector form. Right? This is not important. What's important one is the final step. Now compare the coordinates. X equals to this, y equals to this, and z equals to this. And then I'll just make it from free from lambda, remember. So I'll get x minus x1 equals to, let's write lambda a. Y minus y1 equals to, let's write lambda b. Just compare the coordinates. Z minus z1 equals to lambda c. So therefore x minus x1 by a equals to lambda, y minus y1 by b equals to lambda, z minus z1 by c equals to, say, lambda if you want. You can write lambda here, but normally we never use this, we write this much only. X minus x1 by a, y minus y1 by b equals to z minus z1 by c. This is called the Cartesian form of the line, remember. Cartesian equation of the line. Very important equation, we'll use it frequently. What is this ABC? That represents the direction of the line. X1, Y1 and Z1, that's a fixed point on the line, remember. So if there is a line here, then the fixed point is given by what? X1, Y1, Z1 here, which is vector A. And what's the direction of the line? Which was vector B, if you remember, which were taken A, B, C. And what about this X, Y and Z? That's a variable point. You know that we were using even in R2 also. In R2 we were using X and Y only. So this is very well-known standard form of a line, which is in the Cartesian coordinates form. X minus x1 by a, y minus y1 by b equals to z minus z1 by c. Always you have minus sign here, remember. Fine. And what about this ABC? As I told you, that's nothing but which form? Here components of direction of the line, or vector parallel to direction of the line. And here minus sign is there, remember, in the numerator. That you have to keep in your mind. Secondly, here if I take vector b equals to just ABC, you can choose your LMN also. LMN means what? Direction cosines. You can choose like this also. Instead of just direction of the line, you can choose LMN in that case. So therefore the equation of the line you can write like this: x minus x1 by L, y minus y1 by m equals to z minus z1 by n, where this L, M, N are direction cosine, so L square plus M square plus N squared is 1. Remember, this is always true. So 1 is this, that's called Cartesian form, and the previous one which we have stated, this is nothing but vector r equals to vector a plus scalar into lambda b. This proof is not important, this is just for the information I mentioned. This is known as which form? As I told you, vector equation of the line. Remember, this is sometimes called vector form of the line, vector form or vector equation of the line. Fine. Sometimes you may not be given vector parallel to the direction of the line. Instead of that, you have 2 points. So one is x1, y1, z1, as I told you. You can call the vector A, and the other one is point B. You can call this as x2, y2, z2. So line passes through these 2 points. You can call the vector B here. So we want to write the equation of the line in this case. What's the question? Equation of the line through these 2 points. You are not given here direction of the line, remember. What's given to you? You are given 2 points on the line. Now to get the equation of the line, you need a fixed point. So which fixed point you are given? That is, you can take either A or B. Fixed point is, for example, vector A. And how do you form the direction of the line? The direction of the line you can form direction of the line that you can form either by forming the vector AB or BA. Suppose I am forming the vector AB, which is nothing but what? Vector B minus vector A, remember, you know. So now you have the direction of the line, that is this, and fixed point, and therefore you can write the equation. Therefore equation of the line here, vector r, that's a variable point, equals to that fixed point, that is this vector A, plus scalar lambda into direction. What's the direction? That is vector B minus vector A, right, where lambda is a scalar. Remember, what's lambda there? Any scalar. Scalar means number. The only difference which we have noted here is this one. What? Instead of the direction of the line, you have formed the direction with this concept. Which concept? By forming the vector AB. This is a vector that's a parallel to the direction of the line. You could have formed these also, remember, vector BA also. Final answer remains same. That's not important. So in that case, you have position vector of A minus position vector of B. That's not important as far as direction of the line concerned. You are talking about line, remember. It makes difference when you talk about a vector. Fine. So the only thing we have changed here, that's the direction, or the vector that's parallel to the direction of the line. That is which vector? Vector B minus vector A, remember. That's the only difference. And same way, if you write here, this is a vector form. If I write the Cartesian form, how do I write the Cartesian form? X minus passes through fixed point, x1. Y minus y1 equals to z minus z1. Fine. And what about the direction? That is B minus A. So first component is x2 minus x1. Here y2 minus y1 and z2 minus z1. Remember, that's a Cartesian form of the line, right? This is nothing but what? This comma this comma this represent the direction of the line, which is vector AB, which is B minus A, x2 minus x1, y2 minus y1 and z2 minus z1. Numerator is same. So this is a Cartesian form when you are given 2 different points. Okay, let's go to next theory now. The next theory which you want to write, that's about angle between 2 lines. Right? Angle between 2 vectors, you know. Right? Here we want to write angle between 2 lines. Two lines. Okay. So we have two lines, let me call L1 and L2. They are intersecting lines. So line L1 is given by here, vector R equals to vector A plus lambda into direction of this, let me call that as vector B. Okay, and the other line L2, that's given by here, vector R, this is a variable point. Suppose it passes through fixed point A dash plus scalar, and here this passes through B dash. These are just symbols, remember, this is not important. Fine. So this passes through here, let me write this passes through vector A, here this passes through vector A dash. Here direction of this one, that's given by vector B, and the direction of this one is given by what? Vector B dash. Okay, so we have these two. Now let's take theta be the angle between these two. It's always taken as an acute angle, remember. It's taken as what? Acute angle. So this is also angle between these two, but you can see in the diagram it's obtuse angle. So let theta be the angle between two lines. Angle between two lines. Okay, so it is always acute angle as I told you. So it's from 0 to pi by 2. Now here formula just comes from the vectors only. You recall the angle between two lines is same as the angle between the direction vectors. What's the formula? If you remember, cos theta equals to vector into this vector. So vector B dot the direction vector of the other line, that is B dash, upon their magnitude. This formula just comes from the formula of the angle between two vectors, but with little modification. What's the modification? In the vectors, angle is from 0 to pi. Here it is from 0 to pi by 2 only. So we have modulus in the numerator, remember. That's the modification here. Fine. Now if I take the vector A as for example, let me take the direction is here A1, B1, C1. Okay, and vector B dash as, let's write here A2, B2, C2. A2, B2, C2 here, right? This is vector B dash, this is vector B here. Now if I just place the value here, you have cos theta equals to dot product. You know how to write the dot product. A1 into A2 plus B1 into B2 plus C1 into C2 with their magnitude upon root of the magnitude of the first one. That you know how to write, into the magnitude of the second one, that is A2 square plus B2 square plus C2 square. In the numerator you have modulus, remember this is the formula. The simplest way to remember this formula is this. This is just the formula between angle of two vectors with one modification. What's the modification? You have modulus there. You recall in the vectors you had such formula. If these are the two vectors, for example vector A here and vector B here, then we had this formula, cos theta equals to vector A dot vector B upon their magnitude. In the previous chapter we had this formula. But there theta varies from where to where? You know, 0 to pi, angle between two vectors. Here we are talking about what? Angle between two lines. So it varies from where to where? 0 to pi by 2. So we need to put the modulus. Fine. In short, angle between two lines, L1 and L2, this is L1 and this is L2. It is as good as angle between their directions. This is the direction of the first line. This is the direction of the second line, remember. Fine. So we have the same formula, but as I emphasized number of times, you have modulus in the numerator. Cos theta is equal to modulus of the vector B dot vector B dash. These are nothing but the directions upon their magnitude, individual magnitude, remember. Fine. The next point is distance between two parallel lines here. So I'll take two lines which are parallel. That means the directions are same here. Vector R equals to, this passes through fixed vector A1 plus lambda The direction of this is B. This is a variable, so R is same. Fixed point may not be same. So here vector A2 plus, let me use some another scalar mu here. And here directions will be more or less same, right? So one line like this here, that passes through here one fixed point, vector A. There's another line that's parallel to this, remember. There's one more line that's parallel to above line. This passes through another fixed point here, that is vector A2. Both these lines are parallel to some fixed vector, right? That is nothing but here, which one I've used? That's vector B here. So direction of this is nothing but the vector B. Direction of this one is vector B. Even in R2, you remember, two lines are parallel, their slopes are equal. If you remember, slopes are equal. Where? In R2, which we did in coordinate geometry. Here, when two lines are parallel, then the directions are multiples or same, you can write. Fine, I'm just reminding you from R2. Okay, now we want the distance between these two lines, that is, we want this distance, parallel distance, this one. We want this, right? The distance between these two parallel lines. Okay, so it requires proof. It's not obvious, but I'm just stating the formula. The distance between these two parallel lines, distance between two parallel lines, that's this distance, okay, which is equals to, it's given by this direction difference of these two fixed vectors. Right? You can call the vector AB, for example, or BA, whichever. Vector AB, here your cross the vector, that's the direction of this line, upon its magnitude. Right? That way you can remember. AB cross vector B upon the magnitude of this. That's a unit vector. Some concept of the projection is used here. Now what's the vector AB here? That is nothing but here vector A2 minus vector A1 cross the direction of this line, that is vector B upon its magnitude. Right. This is the formula. You need to remember this. I have just written without proof. AB cross, you can write B cap if you want to write. You can write AB cross B cap. B cap, you know, it's a unit vector in the direction of vector B. B cap means vector upon its magnitude. AB cross B cap. What is AB? Two fixed points on these two lines, parallel lines. Cross, remember here your cross product. In the previous formula you had a dot product. B cap, what's a B cap? That's a unit vector in the direction of the given line. So you need to use this. Once you know this, you can write this very easily, remember. AB cross B cap with magnitude. When you cross product, obviously you need to take the magnitude. Vector AB cross B cap. B cap means what? Vector upon its magnitude. Here one more point about lines, which are sometimes called skew lines. Skew lines means lines which are in different planes, which are also called sometimes non-coplanar lines. Non-coplanars. So two lines which are neither intersecting nor parallel are called skew lines. Means they are in different planes. Remember, non-coplanar lines, they are in different planes. You know, if two lines are in the same plane, then either they intersect or they are parallel. Coplanar lines means what? Either they are intersecting or they are parallel or identical. You know, these are the only two possibilities. Here we are saying that they are not intersecting as well as they are not parallel. and such lines are called skew lines. They are in different planes. So if these are the three coordinate axes, you have here different planes. For example, one line is in this plane. This one line L1 in ZY plane, and another one I'll consider in XY plane. This line L2 in XY plane. This is in XY plane, this is in ZY plane. So these two lines are skew lines. Two lines which are in different planes are called skew lines, or which lines? Non-coplanar lines. That's one thing. Here it's difficult to visualize because I'm showing some 3D picture in 2D, remember, right? But if you imagine here like ground as XY plane and wall as one another plane, then you consider one line in ground and the other one line as the adjoining wall. Then these two lines will be in the different planes and they are called the skew lines. In short, what I'm trying to tell you is two lines which are not in the same plane means non-coplanar lines are called what? Skew lines. Okay, now here we want actually distance between two skew lines, which is sometimes called the shortest distance. Shortest distance between two skew lines. Two skew lines. We want the shortest distance between two skew lines. So you have two lines which are in different planes, non-coplanar lines. So let one line L1 be this vector R with direction as fixed vector A plus scalar into direction of this line as vector B. The another line L2 that passes through the fixed vector A2 plus lambda, or you can use some another scalar. Let me use mu here, and passes through, having the direction as vector B2. Your direction as this passes through this, direction as this passes through this. Fine. Now these are skew lines, remember, that means they are in different planes. These are nothing but skew lines. So it is assumed that they are in different planes. We want the distance between these two. So again, some concept of projection is used here. So I'll write the minimum distance, the shortest distance between these two, that's given by this expression here. Difference between these two, that is nothing but here. You can call vector A2 minus vector A1 dot cross product of these two directions upon its magnitude. So B1 cross B2 upon its magnitude. So this is based on some projection theory here, remember, projection vector. So that's why you have unit vector. You can see that this is a unit vector, vector upon its magnitude. You need to just remember this formula to find the shortest distance between two skew lines. Remember, two skew lines here, lines which are in different planes. So what's the formula? Difference between these two vectors, that is vector A2 minus vector A1. This is a dot product, cross product of these two directions, vector B1 cross vector B2 upon its magnitude. This is like the previous theory only. Remember, here lambda and mu are scalars, remember. These are nothing but what? Scalars here. Scalars means real numbers. Fine. I repeat this, shortest distance between two skew lines, which is given by difference of these two dot cross product of two directions upon its magnitude. This is a formula to get the shortest distance between these two. So that's all in all about theory of the lines. Now in the next session we start with exercise 11.2, which is purely based on theory portion.